Hello, my name is Gong Kai Zhen, and today I would like to discuss about mini project 1. I will wave hand here to. So for part 1A, we are asked to implement this code into the Altera board. So as we can see, there's a 10-bit input and 10-bit output, which is switch and red LED respectively. So what is the concern about this part is that we have to manually, or we have to configure the pin specifically, otherwise it will mess up things. So as I show over here, this is Quartus 2, and where I did from the pin planner, you can see that I made the configuration according to the DE1 manual, attached on the. So let's move on to part 1B. So in part 1B, we need to design a clock divider which will divide the bus clock 50 MHz into between 1 to 2 Hz. So what we will do is by dividing the 50 MHz by 2 to the power of 25, and then we will get a frequency of 1.49 Hz, which is between 1 Hz and 2 Hz, and that is what we want. So I can show over here 1.49 Hz. So we design a module clock divider, and then we will have the clock divider give an output count out, which is 25 down to 0. Okay. So at the simulation here, wait a minute. Is this the one? No. Part 1A. Yeah, this one. Okay, yeah. So at the simulation, let me zoom in a little bit. So in the top level, the clock divide, it will output a count out, and then for the state machine, it will take in the 25th bit of count out as its clock. This is what we do, and then I will show the simulation. We need to run the simulation for a while first. 100 milliseconds. So the output should be start changing at 67 milliseconds, because 67 milliseconds is exactly when the clock is equals, the frequency is equals to 1.49 Hz. So I mean to wait a bit. Alright. So we can see over here the output LED are changed when the time is equals to 67, yes, 67 millisecond. And I will show in the, so it will be faster if I just show in the report. So in report, the clock divider is 25th bit, 26, sorry. It's also updated at 67 millisecond. So it's safe to say that the clock divider is clocking the module with 1.49 Hertz correctly. So let's move on to part 2. So in part 2, let me adjust the camera. So in part 2, we have to design this. We have to design the sequencer, and we can see that this circuit is made up most with the D flip-flops, and the inputs are affected by the previous output of the D flip-flops. Mini 1 part 2. Okay, so these are the cores of D flip-flops, and this is the module of D flip-flops. So these are the output and input. This is the logic operation of the D flip-flops, and then the start is implemented, because instead of just having x0 equals to s4, it will be better to have the s4 XORing with the start to jumpstart the cycle. But this start will only high for one clock period, otherwise it will mess up the coming output. This is a schematic diagram. I can show it over here. So what is concerned in this? So our concern about this part 2A is that we need to know exactly which step it will go for every translation. So this is the state transfer diagram, and then I will run the simulation, and we will found that the pattern are exactly the same with the state transfer diagram just now. Yeah. So as you can see, let me zoom in a little bit more. The start only lasts for one period. And then we have our output result over here. You can see it jumpstart the system so that it changes from 0000 to 0001. So more details are shown in the report. I will not cover much more over here. So these are the logical operation. And then let's move on to part 2B. In part 2B, we need to observe, as we can see, there are propagation delay in every one of the D flip-flops. We have 90 nanosecond and 150 nanosecond. Need to observe how the clock period and the propagation delay affect the output. So as we can see, at the generic map, we will map the propagation delay one by one accordingly. And yes, it is a different logical circuit with part 1. I mean part 2A. So those are changed as well. But let's start the simulation immediately. We will start with clock period equals to 10 first. This is not the one. Yeah, we will start with clock period equals to 10 first. Okay, so run. Okay, so we can see the output is 0 until the end. So there is no change in output. And then we will run in 100 nanosecond. So we can see different with 10 nanosecond of clock period, there are actually change of output over here. This is because the 100 nanosecond of clock period is long enough for the D flip-flops of propagation of 90 nanosecond to output the output correctly. But however, these outputs are not correct because there are 150 propagation delay. So which means that at 100 nanosecond, the 150 propagation delay D flip-flops will not output the output correctly. So let's try 200. So if you run 200, the output will be correct. Yeah, over here. Wait a minute. So when we run 200, the logic will be correct because 200 nanosecond is long enough for both. Is it 200? Yeah. Because 200 nanosecond is long enough for both propagation delay to run. And then the output will be correct. So for part 3, we are going to design a 4-bit ALU. So as we can see in this 4-bit ALU, we have 1, 2, 3, 4, 5, 6 input. We have 6 inputs and 3 outputs. And then we have A and B. A and B will be data, and then mod select will be mod. This mod select will determine whether the operation is in logic or arithmetic. S1, S0 carry in. S1, S0 carry in will determine the operation, its function. Okay, so let me open Mini 1 part 3. Yeah. So in this module, we will be running the input for A, B, S1 and S0 by state machines. So there will be a state machine giving out 4-bit data for A and B respectively, and then one S1 S0 there will be another state machine. It will be faster if I just show the schematic diagram. Yeah. So we can see over here, we have the state machine for operation select, the state machine module for A and B, state machine for A and B, state machine for S0 and S1. Yeah, that's it. So for M and C0, I will manually control it, so it will be convenient to test the things. So this is the top level, and this is where the operation goes. So we have logic select, we have arith select. So when m equals to 0, if we run logics. So logic is equal to S1 and S0, arith select will equals to S1, S0 and C0. But because we are running logic, C0 is not in our concern, so we will just use logic select instead. So we can see after running all of this, after cast selecting, F will output the logic out, which is the output. And for arith select, there's a little bit, we run this, but this is just for the subtraction, because we are running in unsigned. Yeah, unsigned. So if A is lower than B, because in the provided we only can have A minus B, A minus B minus C, so A must be the first. But what if A is smaller than B? So I've create a negative sign. So when A is smaller than B, we will have B minus A instead, and then have a negative sign. And this negative sign will be light up on the red LED to show that it is a negative value. So simulation. So instead of showing the simulation with decoder, I will use the binary instead to show the output. It is much more, how to say, visual. Yeah, this test bench. So when C equals to 0 and M equals to 0, it will run logic operation. Yeah, because we run logic operation, so 0 flag and count out is not in our concern, so there will be no output for them, and the outputs are correct. The desired output are tabulated over here. So if we will go through it, we will find that the output are exactly the same. So I will close this. and then I will run 1 and 1. No, I will run m equals to 1 and c equals to 0. So in this, there will be no involved in c out, carry in, I mean. So we run arithmetic and we get 0 flag when there are 0. And then we will have the output correctly. Then C0, C1. So the output are also exactly as what I wanted. But alright. So at 0, there will be 0, 0, 0. There will be a carry out. This is actually addition, and this one where there is no carry out is the shifting. Yeah. So addition and there is too much, there will be a carry out, but that is only for arithmetic. Otherwise, there will be no carry out. Yeah, the negative sign. I will show the negative. The test bench just now do not have negative sign because there is a separated. There's a separated test bench, but it's still the same, just that it do not involve decoders and LUDR. Yeah. So if we can see there is LUDR light up when there is subtraction where A are smaller than B. So these are the decoders. We will output the accordingly to the decimals counterpart. So yeah, that's all. Thank you for listening.